I think most of the folks who are here know you, Michael, but some may not. And this is an interesting part of work, separate from your SRI work, but it's, as I said earlier, it's nice to have all of these blinky lights in an AIC seminar. A lot of times we don't get hardware stuff in here, so I think this is pretty cool. Anyways, I'll hand it over to you.
Right, yeah, thanks all for attending. So this is my talk, Re-engineering of a Historical Educational 4-bit Microcomputer Trainer with Arduinos. And as Aaron just said, so this is basically a talk from the hobby lobby, right? So it's not SRI work, so I have plenty of pictures, you know, and I hope it's going to be fun. So some motivation maybe, why this talk? First of all, it's a little bit AI off topic, of course, right? So the focus here really is basically somewhat a maker focus, electrical engineering focus, right? So I'm talking about this historical educational 4-bit microcomputer and how I and my team re-engineered it over the last 6 years with Arduinos, right? But then, I mean, single board computers or SBCs, right? They are not entirely uninteresting for us. So given that we now have these edge computing devices like NVIDIA Jetson and so on, right? So as AI folks, this is certainly also something for us to be aware of and interesting for us to look at AI single board computers, right? And then we also had seminars, of course, about coffee and chocolate in the past. So why not about Arduino tinkering, right? And last but not least, Karen also encouraged this presentation. So that's the main reason why I'm giving this here, right? So why might you find that interesting, this talk, a little bit, and what could you get out of it, right? So, I mean, it's in the interaction of retro computing and Arduino tinkering, so to speak, right? I'm trying to give you a window to the past, a little bit historical context, right? What was home computing?
I'm at a seminar now, and then a few PSs to open. I'm going to go there to return some.
Okay. What was home computing like in the late 70s?
I'll let Tony know.
80s?
Andy, can you mute, please?
Thanks. So yeah, I mean, I think it's always got to you know, look into the past, you know, to learn from the past, to understand how we got where we are. If you enjoy going to the Computer History Museum, right, then you might also enjoy this talk a bit. And I also feel that we are at a place where computing history matters, of course, with all the great history that SRI has in creating basically the modern world of computing, right? And then maybe you can relate your personal road to computing, how you got into computing, into your career, and your first computer, and maybe you're a little bit like me, that you still have some emotional, nostalgic connections to these old machines, right? So, but mostly I don't only want to, you know, talk about the past, but maybe get across that the Arduino platform is a great platform for these kinds of EE ambitions and tinkering, right? So it's really a fun platform. So that's the re-engineering target we have, right? So this was my first computer, the Microtronic computer system from the company Busch. That was released in 1981, but somehow designed in the 1980s, right, with the help of Texas Instruments. And so to add to the suspense, right, I'm not opening the box yet, but later. So this box actually shows an early prototype board. So that's not the final board that they actually put in production and sold then. So, and then of course the Arduino, this is when one hears Arduino, what most people think of, the Arduino R3, right? The Computer History Museum considered it important enough to put it on their timeline of computing, right? So the first Arduino was released in 2005, which is a modern microcontroller that you can program in C. And the Arduino IDE is basically a platform which by now supports a lot of boards, a lot of drivers. There are a lot of tutorials and a great community around this, right? So this is basically the microcontroller of the maker community, if I may say so. So yeah, I started in 2016 basically with an Arduino, right? With a big mess of wires. And then in 2019, I got a team, and so I submitted a re-engineered version, basically, where we then had a custom printed circuit board, right? And a little bit something more professional looking to the Hackaday reinvented retro contest. And in 2021, we won a prize for this. So I then accepted the prize for the team and shared it with them. And so this is what Karen brought up in the end of year party, right? So that was the retro challenge contribution, which I submitted in 2021, and we also won a prize for this. And so, so the outline of this talk is I want to tell you a little bit about the whys, the motivation, right? Then the what's, so basically what kind of machine is that, right? And give a little bit of historical context. And then, of course, the hows, basically. So those are basically here the 10 different versions that got created basically over the last 6 years since 2016, right? So let me maybe start with the whys, and yeah, and start with a little personal anecdote how I got hooked by electronics, basically. So maybe like some of you too, as a kid, I of course like to take apart to the frustration of my parents electronic devices in the house, like radios and tape recorders, and open them up. And usually I was able to get something out of this, right? At least I learned a bit about their composition, right? Could identify transistors and resistors and things like this, right? And at some point then I opened up our Texas Instrument TI-30 calculator. And what I saw inside there, really that kind of shocked me, right? Because it was really only a single chip and the bubble LED display, right? And so I had expected to learn something from actually opening it up, right? But I didn't, right? Because it was like opening basically a present, a box for your birthday, and then only to find another box inside that box, which was actually locked, right? So couldn't go further with that. And then at that point, I thought, okay, that's beyond comprehension. That's like finding an alien artifact, right? I really need to understand a little bit more what that magic behind that technology is, right? And I think this is how I got hooked by electronics when I was 11 or so, right? So yeah, then I actually recreated this machine then 10 times, my first computer, right? Some with my team. And it's a little bit, of course, like, you know, Groundhog Day, by the way, which is today. Happy Groundhog Day. Like one more round, right? So mostly nostalgia, but then also the educational aspects, right? And also doing Arduinos with the kids as a STEM activity first, but then I also got into Arduinos and I found it very intellectually satisfying and also a highly creative process, right? Because there's so much basically that this Arduino platform has to offer in terms of different boards, in terms of different modules, right? And these things are all fairly inexpensive, right? So you just keep buying modules and there's always one more thing you want to try. So you're a little bit like a kid in a candy store, basically. At least this is how I felt, right? And another thing I wanted to explore is basically the what ifs, right? Given that this was such a limited machine that I had there in 1983, right? I figured, what else can we do with the Arduino platform to extend it a bit, right? For example, can you add an SD card basically instead of a tape recorder for program storage, right? Or can you add a speech synthesizer, right? And the company actually had announced a speech synthesizer at some point for the machine, but it got never released, and I guess for good reasons. So, because it didn't really make a lot of sense to have a speech synthesizer for this kind of restricted machine. And so all kinds of extensions, the what ifs I wanted to explore, right? And how to realize this, basically these new features in a historical architecture. So why would your parents have bought you this machine in the early 80s? So I think the big point is, of course, the price, right? It was much more affordable. So it cost 380 Deutschmarks in 1981, right? And later the price got reduced to 299. And considering that the average family income in Germany at that time was around 32,000 Deutschmarks, right? So this is 1/80th of your annual income, right? So that is much more affordable. So if you look at other machines, home computers that were available at that time, for example, the TRS-80 Model 1, right? You would have had to pay 1,995 Deutschmarks, and that's already 1/16th of your annual income, right? So it's a very, very big price tag. And similar for other machines, right? Apple II was, of course, even more expensive. And if you compare this to the prices in the US, right, then the average income there was $23,000, right? So US citizens only had to pay like 1/27th of their annual income to get a TRS-80 Model 1, right? Then the prices dropped significantly in 1983, which was known as the home computer price war, right? So there was a total market crash and the machines got really affordable then. But before that, it was still a very expensive business to get into home computing. And of course, this is really an educational machine. So computers were the future. There were excellent age-appropriate manuals for kids, right? Even containing illustrations, things like that. And the focus was, of course, less on video games, but more on physical computing, right? Was also a natural step up to, say, science fair electronic kits that kids would have had, right? That were STEM affine or interested in electrical engineering. And of course, you didn't require a TV, and it's just so built for physical computing on experimentation. So there's less danger, of course, than damaging the machine, right? So that such a machine was still a bit of money, right? So those are some prices basically from back in the day, right? So see that then Apple is like almost like 3,000, 4,000 Deutschmarks. The only other thing that would have been close in price is something like a Sinclair VX81, which you could also get as a kit in 81 for the same price tag. But I must say I preferred actually the machine that I got because it was more experimentation friendly.
I have one of those.
You got a ZX81?
The Sinclair.
Yeah, I think in the US it was called Timex 1000,
That's
right?
That's
Yeah.
right. That's right.
Sinclair was the British version of that.
I might still have it.
Yeah, it would be fun to fire it up again, right? So I also have a bit of a collection of old vintage computers or retro computers. Those are my TRS-80 home computers, the Model 1 on the left and the Model 4 on the right. And a little bit of a fun fact, see this monitor here on the Model 1 in the left, right? That's actually produced and mass manufactured by RCA, right? I guess, which would be SRI Princeton, son of these days, right? And so basically the design of this monitor, right? All they did was they offered it to Radio Shack and said, okay, we can just paint it silver for you because it had this wood grain TV design, right? So, and then the design of the rest of the computer was actually determined by that monitor, right? See the ventilation grill and so on. So that was then matched the design with the computer and the expansion interface. So I thought that was just a fun fact given that we had SRI. So the what's. So, okay, enough suspense, time to open the box, right? And let's have a look at this board. So what we see there on the right is, somehow my mouse pointer is not showing up here. What we see on the right is the CPU, right, which is a TMS 1600 microcontroller from Texas Instrument. And then right to it in the socket, there is a static RAM, right, with a couple of bytes for the program memory. And then on the left, you would have something like a cassette interface that would allow you to store and load and save programs to tape, right, to the tape recorder. And then, of course, you could only program it in machine language, right, and you would have a bubble LED display. So, so the monitor program that then allows you to enter and run and debug these machine programs is available to you, and so it allows you to enter programs, right, to inspect programs, to run and programs, also to inspect and modify the registers of the machine, to set breakpoints, also single stepping, things like that. And the address range was 1 byte, right? And you see this here on the left, 1 byte address range. Of course, that's ridiculous. and then a 12-bit instruction word, right? And then the machine also had carry and zero flags for branching, right, in comparison. So I have a little video that now shows you the user experience. I hope that shows smoothly enough. So that is the real machine, basically, right, from 1981. So first thing I'm doing here is I'm opening the lid and I push the reset button, right? And now I'm entering a program. So I'm setting first I'm clearing the memory. And then hold next 00, I'm entering a program, machine code. I'm saying clear all registers, display 3 digits on the display starting at register 0. So it displays register 0, 1, and 2. And then I'm adding 1 to register 0. I'm borrowing a carry, and so this is a 3-digit hexadecimal counter, right? So this is a go-to, and then starting the program, you just see, let's see, I made a mistake actually. So I put a go-to to the beginning where it clears the registers. So I corrected this here, and now I'm starting the program again, and you just see, okay, it's indeed running the 3-digit counter, and you see how ridiculously slow that machine is, right? So another thing then is you can easily output a register to the digital output ports at the end. So I put in one more opcode here at the end of the program, and you now see that the LEDs are showing the register content of the first digit in binary, and that way you can basically easily drive external digital devices, right? So you can also inspect the registers and change the register values. So here I'm setting the start value now to 500. And if I start the program again by going to address 2, then it starts counting at 500 because I modified the registers before, right? So yeah, that kind of user experiments you would get from these early microcomputer trainers, right? So those machines existed for all major CPUs, right? And they could all be programmed with a monitor program like this and a machine code language, right? So yeah, and it also has some built-in ROM programs. I'm playing a game here, but okay, so much for that. If that's not entirely clear, I guess that doesn't matter so much. I just wanted to bring across the user experience. So next slide. So you can of course say, well, is it a toy? And I would say yes and no. So the instruction set, I mean, consider you only have like 1 byte of address range, right? That's really not that much. And in order to write any serious program, you would need a very high level instruction set for the CPU, right? And then if you look at the programs that were available for this machine, then many of these programs you could also find for other single board computers of that time, something like the NIM game, right, or biorhythm computation, even something like a lunar lander or prime number calculation, tic-tac-toe, things like that. And so a more mature, more advanced trainer would have been this microprocessor board on the right here, which had a real Z80 CPU, right? But I mean, you would have had to go to greater lengths in order to get the same kind of programs with that machine, right? Because Z80 machine code is kind of less dense, and the machine language instructions are kind of less high level than what was offered by this educational Microtronic computer, right? And that is what enabled you to write fairly complex program. For example, something like a lunar lander program, right? This is from the manuals here, fairly complex, right, program, and kid-friendly illustrations, little comics. So, and of course, I mean, if you want to recreate Doc Brown's automatic dog feeder, then you could do this basically with such a machine, because you had, it was set up for experimentation and physical input-output, right? So you could, for example, connect a relay, and the manual also had experiment for that. So there's a built-in real-time clock, for example, and you could basically program an alarm clock, right? And with a relay, you could even then connect, equipment that would require 110 volts or 220 volts to the grid, right, and control it over your Microtronic. So the company was really big. This company Busch that made that was really big in electronic kits, right? And so this was their platform basically. Very nice experimentation platform, I think, and some fairly advanced modules. So even something like a synthesizer module here, right? You could get, or TI chips in the usually. So in 2016, then, so this was basically the what. So now you know the target machine, right? And in 2016, I then started tinkering with Arduinos, and I created some hardware extensions, basically just with standard off-the-shelf modules. For example, I created the speech synthesizer that I always wanted to get for the Microtronic, basically connecting it to the input-output to the output ports, right? And then having an external Arduino R3, Arduino Uno, that would drive an AMIC2 speech synthesizer, right? So that way I could then send basically ASCII data over the 4-bit output port, nibble by nibble at a time, right? And assemble the string on the Arduino side and then send it to the AMIC2 for utterance. And I also built a SD card program storage basically. So I would no longer use the tape recorder for loading and storing programs. Yeah, so a little bit of a historical window. I mean, homebrew computers, and we already talked a little bit about this, Aaron and I, right? Was a common hobby in the late 70s and early 80s, right? And I would say it's still a popular hobby nowadays. So if you look at the Hackaday communities and all the homebrew computer projects that you find there, it's quite amazing what people are doing, right? And I would say it was never really very difficult to build your own computer, even back in the day, but it was still kind of pricey, right? And especially not everybody had the required equipment and tools and skills to do that. So even putting together kits together wasn't possible for everybody, right? So of course some famous, computers, the Altair 800 was released in 1975, I think, right? And then also RCA, right, released something in popular electronics, the Cosmic Elf.
Yeah, that's our 1802 processor.
Yeah, CDP something, right? And
yeah, it's a CMOS processor.
yeah, so I think that's also an RCA SRI Princeton invention, basically, right?
Yep. There's some of the deep space probes have those on
really?
it. So at JPL, there are still people who program the 1802 to get programs up to the deep space probes.
Yeah, that's kind of cool. I mean, I guess CMOS, I mean, it runs forever, right?
That's right. That's right. Yeah, and interesting registers.
Yeah.
I had a friend who had the KIM. So the KIM is based on a 6502, which
right.
is the same
The
processor as the Apple One.
Right.
And the folklore is that very few people got their Altair 8800s working.
It was a difficult process, right?
Yeah.
And you had to spend hundreds of dollars, and then in the end, it wouldn't work, right?
That's right.
Frustrating, yeah. So yeah, then in 1977, the home computer revolution. Then suddenly one could build off-the-shelf, consumer-ready, right, products like the Apple II, TRS-80 Model 1, and the Commodore PET.
So the Homebrew Computer Club met off of Marsh Road. No, there was another one. That was off of Marsh Road.
Did you attend back in the day?
No, I wasn't here then, but you can find their newsletters and stuff online that have the address.
Right. Yeah, and interestingly, I mean, the TRS-80 Model 1 also started there in the Homebrew Computer Club here, right? I don't know which one now, Slack or the other one.
I think it was the one off of Marsh Road, actually.
Right. And of course, we all know about the Apple I and Apple II. So, yeah. And then, I mean, okay, so I built my own computer, but what does that really mean, right? So I would say nowadays hobbyists have many more options, of course, and things got much more affordable. So even an oscilloscope or so you can nowadays get for $200-300, right? And so if you want to get into that hobby, it takes much less money to do so, right? And then there are many ways you can build your own homebrew computers these days, right? So the question is, of course, on what level did you do that? So you can say, okay, I built my own PC from off-the-shelf parts, right? That's not really what you usually mean with homebrew computers, but so here the focus is more on retro computers, right? So you can either use a classic standard CPU like a Z80 or a 6502. You can either use an old CPU from back in the day, or those CPUs are actually still available as modern parts still, right? So they're still being made. And it's a popular hobby, for example, to build your own CPM single board computer that can run on a Z80, right? That runs BASIC, right? If you look at all the stuff on Hackaday, right? So yeah, some folks are even crazy enough to build a custom CPU, right? Maybe from discrete TTL chips, right? 74 LS something, or even transistors. You find these projects on Hackaday too. And then another route, and this is the route that I went here, is of course then software or hardware emulators, right? You can have a pure software emulator that only runs on a PC or Mac, right? Or you can use embedded software and write a program for a microcontroller or Arduino or FPGA, right? And that's the route that I took here. And I would say, if you don't require high fidelity, right, or you accurate timing, right, of the emulation, and you don't need to emulate basically the signals of the chip, right? I know that SRI's microcircuit emulation center is doing that, right? They are really reproducing the chip and doing timing accurate emulations of the signals of the pins, right? That's of course very difficult if you want to do this accurately, but you don't have to do this if you only want to run a embedded system that runs the original software, right? So yeah, now we come a little bit into the how section. By the way, what's the time? I think I still have some minutes. Oh, it's only 4:30, so okay, I don't need to rush that much. So how did this company actually pull that off, right? In 1980, 1981, when they developed that system, right? So one has to consider the design objectives, right? So it had to be inexpensive, right? And you wanted to keep the machine language simple and kid-friendly, right? But yet powerful enough so that you could run real programs in a very restricted address space, only 1 byte. And the answer is, I guess, microcontrollers, right? Back in the day and today. So if you use a microcontroller instead of a microprocessor, then this reduces your circuit complexity and hence costs a lot, right? So because a microcontroller is basically a computer on a chip. This is what TI got the patent for, actually, right? Computer on a chip for the microcontroller back in the day. So you don't need extra RAM chips or extra ROM or extra I/O circuitry. That's all already on board of the chip, right? And this is, of course, greatly cutting the costs. So I guess that company then went to Texas Instrument, right, and got some help from them, and they settled on using the TMS 1600, which is a microcontroller clocked at 500 kilohertz, right, which is, of course, ridiculously slow. It's not megahertz or gigahertz, it's kilohertz, right? So it's half a megahertz. And so the CPUs and that they implemented there is actually an emulated virtual CPU, right? So because they needed a kid-friendly and powerful machine language, and the virtual CPU model, which is implemented in this machine, has nothing to do with TMS 1000 machine language, right? So it's completely different. So I already said, okay, it basically has a Harvard architecture. So it's 1 byte of address space of 12-bit words. You cannot write into a program memory, but you have register memory, right? You have 32 4-bit registers. And that's the only writable memory that you have for your program, right? But 32 4-bit registers, I mean, you can already do quite a bit with that. And then the machine language is quite powerful, as I already said, and has some powerful instructions. For example, multiplication, division, a clock, real-time clock command, a random generator, and then input and output commands. All of this would have been tremendous or much more effort to implement on a Z80, right? With, you know, subroutines in the firmware or whatever. The machine doesn't even have a stack, so that's something that they inherited from the TMS 1000, which also didn't have a stack. So you can only have a single nested subroutine invocation call return because you don't have a stack, right? And so I would say that this was a fairly good exposure to machine language programming. And the drawback of this, of course, being that the knowledge the machine language knowledge is not transferable to other CPUs, and right? Unlike you would have learned Z80 or 6502, that would have been something you could have used somewhere else. Actually, there is a somewhat similar predecessor, right? And this is a US design, 1976, from Tandy Radio Shack, the science fair microcomputer trainer. I'm wondering if any of you guys maybe had one of these in your younger days, right? But basically, they went a very similar route. They used the TMS 1100 microcontroller, 400 kilohertz, and it's actually a single chip design. And so this microcontroller came out in 1974, and this educational computer came out in 1976. So I think that was quite a revolutionary STEM toy back in the day. So if you compare the science fair virtual CPU to the Microtronic virtual CPU, then they are completely different, interestingly, even though they run on the same microcontroller architecture, right? And again, both the Microtronic as well as the science fair have nothing in common with the native TMS instruction set. So this microcontroller, right, of the TMS 1000 line was actually something that was invented by TI in, as I said, in 1974. So this is a patent that they got in 1977 then. It's largely forgotten nowadays, but back in the day it was, I think, quite revolutionary and also hugely enabling, right? So all of these electronic toys that are listed here, like Simon or Merlin, Speak and Spell, or that Tomy Big Track, or the Texas Instruments Little Professor, all of those were powered by one version or the other of the TMS 1000 microcontroller. And those electronic toys didn't exist before the microcontroller, right? So it would have been nice if I could have just, you know, read out the original firmware from the TMS 1600 microcontroller. Unfortunately, that's not possible, right? Because something like Flash EEPROM, right, or Flash memory didn't exist back in the day. So those were mask programmed microcontrollers. So you would send your program, basically your mask ROM to TI, and then they would manufacture a batch for you, right? So there's a guy, basically, Sean Riddle, who has a website. And, you know, if you really want to retrieve the firmware of an old TMS microcontroller, right, you can send in your chip, and then he will actually decap the chip, right, and read out the matrix, right, the ROM matrix, and send you back a ROM. But of course, that is a destructive process, right? You will lose your microcontroller. And on his website, he has a lot of firmware of many of these old devices for Simon, Merlin, Speak and Spell, and so on. There is no Microtronic firmware yet. Maybe one day I really send one in, but I don't want to sacrifice it because it's a fairly rare thing, right? And you can't get it back. Good. So the only option that I had basically was no original firmware is available. I also asked TI whether I would still have the tapes or the mask ROMs, right, for the stuff that they produced for the customers in the 70s, 80s, but it's lost to history. So I basically had to re-engineer the firmware just by writing a C program and write a CPU emulator as well as a monitor program in C, right? And so that was then my first iteration. I just used the standard Arduino Uno and one of those off-the-shelf LED and key modules and a keypad. After I had the software recreated, the firmware re-engineered. And with that, I then could basically run my first original Microtronic programs on this emulator. And it's all off-the-shelf modules, right? So just connected over wires. So it would look like this, not very professional, but it worked. So I could enter programs and run them. And also the digital outputs from the Arduino would already work and be good enough to drive some simple circuits. And so, yeah, I would say it's not very difficult to write a CPU emulator in C. So basically, of course, you need to manage the state of the CPU. You need a couple of flags like carry and zero, state management. Then you need some byte arrays basically for the RAM, for the instructions, right? The address space. And maybe you need a stack, there's another array there. A couple of registers in this case, 32 4-bit registers. And that's all not really optimized. So this is really put together quickly, the C code, right? You could save a byte here or there, but I didn't have to because the Arduino had more than enough space to basically accommodate this firmware program. And yeah, basically to interpret now, to emulate a CPU, what you do is you use a program counter, get the instructions that's on the right here. I'm sorry that I don't have a mouse pointer. You basically decode the instruction and then you just implement basically the effects of the instructions, right? On the right, you see line 1524, for example, move for a copy operation, right? Basically copy one register, the source register, into another register from S to D into the destination register. The opcode for this is 0 and then source register, destination register. So 0, 1, 2 would copy from register 1 into register 2. And then you just program this in C code, right? And you set a flag. So if you copy the 0, then you set the 0 flag and so on. And you do this for all the instructions, right? For the whole instruction set. And you basically have a simple CPU emulator, right? Really not that difficult. But again, I want to point out that some of these opcodes, some of these instructions are quite high level. For example, you can, with one opcode, basically you can convert from decimal into hexadecimal or from hexadecimal into decimal. You have an opcode for random numbers, for a clock, and even for multiplication and division. That would then group, since we only have 4-bit registers, right? That would then group like 6 or 8 registers, and you could actually implement a real calculator basically with the instruction set that you had with 6 or 8 digits, right? Of course, no floating point, but I mean, you could do some serious calculations with that. So, second iteration then, and I mean, I have all these versions on display here basically, but eventually I then thought, okay, it would be nice if I could also store programs on SD card, and I got one of these modules. Basically, it's called an Arduino Shield, which has an SD card reader as well as an Ethernet connector, right? And that you can just plug on top of a standard Arduino module. And so I got this SD card shield and another shield basically for an LCD display. And the firmware then grew quite a bit larger from 2,000 lines of code to 4,000 lines of code because I needed to accommodate all the drivers now for that, right? So I needed to switch to a larger version of the Arduino, which is the Arduino Mega 2560, which Aaron, you know well, of course, too, right? And yeah, so this version then looked like this. So I was then able to use an SD card for program storage. And the nice effect of that was that I could plug the SD card into my PC and also edit and change programs there, right? With a text editor, put it back on the card and run it on the emulator. And then on the right, there's a little breadboard, just a reset button and things like that. Yeah, but eventually I wanted to have something a little bit more presentable. So I moved away then from these Arduino shields and got more standalone modules basically. So in the end, I also wanted to add this speech synthesizer and have a more presentable and more durable version. So this version is actually on display here. I produced an acrylic laser cut front plate for this so that it would look a little bit nicer. And yeah, just a couple of different components. But overall, it's still the same second version, right? Just with off-the-shelf display modules now instead of the shields. So here a couple explanation of the front panel. So I wanted to add this LCD display not only for the SD card, so I could look at the files on the SD cards, right, the programs, but also for debugging. So you could actually see the register contents as well as the mnemonics of the machine code instructions of the program, right? And I wanted to keep the user experience like in the original, so right? So basically LED, 7-segment display and hex code, right? So this is really only for debugging and the SD card and for, yeah. So, but internally it's still like a bit like a big mess of wires, right? So you see the different modules that are used for this here. But well, I guess there's still one shield left, which is the SD card shield, but the rest is now no longer shields. For example, I have now these LED displays, which are actually I2C devices, right? It's a serial interface, basically. So, yeah. And I could then also connect do the original experiments with this basically from the manual by connecting electronic circuits to it from the manual. So yeah, that was basically 2016, and then I set it aside, right? And so something funny happened in 2020. So I had all my source code on GitHub. It was an open source project, and I also had a Hackaday page and some YouTube videos. So somehow a bunch of other enthusiasts found me in 2020, and the guy from Belgium, Frank de Jager, and one from Germany, Manfred Henf. And they contacted me, and their proposal was actually to really recreate something more authentic to the original Microtronic. So their proposal then was basically use one of these old electronic kits consoles, you see there on the right, and create something that would neatly integrate into these. You can get those on eBay, right? And for a few dollars basically. And then we basically needed a display that would fit into the space where the VU meter is, right? And the keyboard could be on top of that space there. So again, since the space was very confined there, we now needed smaller modules basically to accommodate all this, right? So Manfred Henf was doing the 3D printing, right? And so, for example, this custom keyboards that they designed, 3D printed, right? And Frank did the electronics and the circuit board design, and I did the firmware. So it's based on my old emulators, basically. And so that's the CPU board that Frank designed, right? So the Arduino in the middle there is the Mini Pro 2560. You can get such a module for $8 or so on eBay or AliExpress or whatever. Very inexpensive. And then also these SD card modules you can even get from Amazon also for a couple of dollars basically. And Frank made sure basically to really accurately recreate the original digital outputs and inputs of the original so that it would be maximally compatible with the original experiments, right? So he even put in discrete transistor drivers for the outputs and so on. Here's another picture. And then you see the input ports on the left, in1 to in4 and 01 to 04 for the output ports. And I also have this version on display here in the room. And some experiments. So here the focus is really, you know, integrate as neatly as possible with the original Busch electronics kits, right? And have an authentic experience. Yeah, so given that they used a different display, I actually had to do quite a bit of refactoring, and I needed to recreate my original version so that I would have something for firmware development. It was again a big mess of wires, but it was just for development. Yeah, so this machine was called the second generation Microtronic, right? Because basically it could have been something that the company Busch would have sold maybe nowadays, right? But of course we didn't try to sell it to them. So it was a good success, I think. So there were like 10 or so other electronic kits enthusiasts that build actually their own, and Frank and Manfred, they supply do-it-yourself kits to the community, and people could do their own 3D printing of the parts and so on. So that was all fun, but I also wanted something more portable and more compact. So in the meantime, I had also learned how to do my own printed circuit boards with KiCad, right? And I wanted to create something that is portable, basically. And I thought, yeah, there were also some missed opportunities. For example, a real-time clock module, battery powered, was still missing, and that's again one of those I2C devices you can get for $5, right? And I thought, let's add that too, and also add a loudspeaker and add some opcodes for doing sound, basically. So I tried to convince the team to submit this to the Reinvented Retro Contest 2021 at Hackaday, right? So this version here, right? But somehow they didn't want to do that. So I then instead submitted my version, right? Which is now something I call the next generation pocket Microtronic. It has the same Nokia LCD display here, right? And it's the same hardware as the second generation Microtronic, but much more compact. And it also has a real-time clock and a loudspeaker. And for this, we then won this prize, right? And so that was a little bit more competitive than the Retro Challenge prize. So there were like 100 or so contributions, submissions to that contest. I then, given that it was also largely inspired and worked out with the team, the display, the Mini Pro and this, I then shared the prize and I accepted the prize in the name of the team. And so that also then plugs into a real Microtronic, into the cassette port basically, and you can use the SD card also as an emulator for program storage, right, for the real machine. And then, of course, I also wanted to try one more version, right, this time with an OLED display, because the Nokia 5110 display, by the way, that's from these old Nokia phones, right, cell phones. They are available for a few dollars as well on the second-hand market, like dozens of them. I guess when all those Nokia phones got recycled, somebody basically recycles the displays and is selling them to the maker community, because, I mean, there are Arduino drivers for this, right? But the display is nice, right? The blue LCD, but it's kind of laggy also because it's LCD. And so an OLED display such as this, it's a SPI bus display, right, is much more reactive. And also, yeah, it just looks sharp somehow. So one more round. Yeah, so whenever I thought I was done now, right, then in 2021, another enthusiast contacted me. This time Eileen, codename Lily, picked up the old 2016 Uno-based version from the GitHub repository, and she started to build her own version, right? So this is her creation here on the right. So she used this really nice retro old Aqua photo box, right? And put it all in there. I think that looks really cool, especially if the documentation is, the PDF is on an iPad, you know, if the paper is actually, the manual is much more advanced than the computer. So, and yeah, she found some bugs and she wanted to add some features that I added to the newer versions, but were missing from this old code. So she asked to work on this together. So I then worked with her together to basically create one more version. So this one is also on display here. This was then my prototype. Basically like the first version that I had, right? But I didn't have the first prototype anymore that was disassembled by now, so I had to build another one just to work with SIR on the old 2016 code base. So yeah, and then I thought, okay, so now finally we can wrap this up. I really want to have a final version which is very close to the original. And I thought, okay, by now I know how to do printed circuit boards, right? And I would like to create something basically without LCD or OLED displays. I really want the original 7-segment experience, right? LED displays experience without any, more modern displays. So I set out and made one more version on a prototype breadboard here. Originally, I used these 7-segment individual LED displays, and you see those are quite a big mess of wires to hook up correctly, right? And eventually then I found a very nice display from Jamaica, which is really the original LED 7-segment bubble display. So I bought a whole bunch of those, right? I guess new old stock, no? And with that then I basically created one final version here, an SMD printed circuit board, which no longer uses any modules, right? And so this is basically what I always wanted to do when I was a kid, basically learn how to create my own printed circuit boards, right? And not use modules. So this is a surface mount device circuit board, right? No longer through hole components and no more modules. And I had to use a surface mount device, so there are no holes here for the legs of the ships, right? So you have to basically use a hot gun and solder them with solder paste onto the printed circuit board. And the reason for doing SMD here was because some of the ships that I had to use were not available as through hole, right? So mainly the display controller here, which is a I thought I have the name here, TM something, TM1683 driver ship, right? So that's only available as SMD. So yeah, so that's then really the final version, right? And given the bubble LED display, it's really very authentic. The user experience is very similar to the original. This is what I really wanted to have, and it's also battery powered. It no longer uses an SD card, but it uses an electrical erasable PROM, EEPROM. So 256 kilobits, and I can just basically store 42 full memory dumps of this machine and use this instead of an SD card for programs. Yeah, so then I also thought, okay, would also be nice to do something, see if one can actually do something more modern with that, right? And for the reinvented, for the retro challenge, I then thought, okay, maybe we can make something like a drum computer out of this, right? And submit this to the retro challenge. So I connected a MIDI drum module here. Actually, it's a MIDI sound module, right? But it can also play drums. Connected this over one of the output ports. It's an UART, right? A serial interface, TTL. And then I needed to figure out basically how to extend the firmware and the instruction set of this historical virtual Microtronic CPU such that I could actually write a Microtronic drum computer, a pattern sequencer basically. And for this, I had to extend the firmware a bit. But in the end, I basically had a drum computer, right? And it's also on display here. So yeah, so I then submitted this to the retro challenge. And this contest is known for mainly this computer by now. The RC 2014 was the winner of the retro challenge in 2014. So that's an annual contest that's being organized by, I think, the Australian Computer History Society, something like that, right? And So this machine, this winner in 2014 got very popular in the UK. And so that is the RC 2014 winner, right? You can get all these different modules for the single board computer, like input-output module, RAM module, CPU board, CF card module, and what have you, right? It's a very popular hobby in the UK. And there are stores here where you can buy these, right? And our contribution then was one of the winners in 2021. And so the prize was this very nice mouse pad, which they always have good humor, right? Very British sometimes. So I guess this is the boss here, and this is your team having to work with the retro computers, and let's boss it. So the boss is giving them a hard time. Well, understandable. So yeah, okay, that's about it. So maybe let's wrap that up. It's 5. So what can we learn from such a Microtronic? I think a lot, right? So in 1981, you could learn hex and binary number systems, the basics of machine language programming and algorithms, general purpose input, output, right? The basics of physical computing, basic computer terminology, what is the CPU, RAM, ROM, I/O, and so on. But of course, there are also a lot of things you cannot learn from such a machine, right? One thing that this Microtronic virtual CPU does not offer is advanced addressing modes. So it only offers basically direct register and immediate register addressing, but you have neither index nor indirect addressing modes, right? And some things like recursion, right, you cannot even implement because there is no stack. And since the RAM is basically Harvard architecture, and you cannot store and restore the register context, right? So with that, of course, there's also no way of really implementing recursive algorithms and things like that. No self-modifying programs, right? Which actually that might not be too bad. Of course, this is also not the fastest machine and only 4-bit. Things like interrupts, direct memory access, or modern communication protocols, I2C, SPI, or UART, you could also not learn, right? And no high-level programming languages. So yeah, let's wrap it up then. I mean, well, conclusion, takeaway. So at least on this level, I would say that hardware is frequently just software, even, I mean, nowadays, even on lower levels, right? So, I mean, CPU architectures like ARM is, for example, is the world's dominant CPU architecture these days. And this is an entirely IP-based licensing business, right? Intellectual property cores, right? And Verilog designs and so on. So CPUs are all basically the software in a sense, right? And many microcontrollers, of course, everywhere. And interestingly, that has always been the case in the late 70s, right? As I tried to show with the TMS microcontroller, right? So it's just complex firmware running on microcontrollers. And I guess that holds true of many devices nowadays, right? I mean, many Linux computers, of course, as well. So Arduino is a great learning platform and stepping stone. I think it also allows you to step up your game and sharpen your teeth as a maker. So you can start with a big mess of wires and off-the-shelf modules, but as you sharpen your teeth, you can go to breadboards and then eventually learn how to design your own printed circuit boards, right? And basically dump the Arduino modules completely and put an 80 mega AVR microcontroller chip directly on your printed circuit board. It's also quite amazing that EDA, right, the electronic design automation process, right, enabled by tools such as KiCad and especially the PCB printing services such as OshPark, PCBWay, or Seed, right, now really enable makers to do things which would have been completely impossible 10, 15 years ago, right? So basically you can create your own PCBs and devices and send off the Gerbers to one of those PCB printing services, and you get them back in the mail, right? And it's really a magical moment when you get your 3 PCBs back from Busch in the mail, and you unwrap the envelope, right? And you have your self-designed PCBs in the hand. That's really a magical moment, right? And it's quite a neat hobby, so I can recommend this, yeah. So, and there's of course a great community. There's a lot of open source available, right? And PCB printing is really affordable these days, and that wasn't the case 15, 20 years ago. So, I mean, for example, for 3 PCBs such as this, right, it cost me like $80 from Busch, right? It takes about 3 weeks to print, and then you get them back in the mail. And if you go to Chinese manufacturer, Seed, for example, or PCBWay, then that costs like, you get 10 PCBs or so for like $30 or so, right? So it's really, really affordable. Okay, so I guess that's what I wanted to share with you guys. And if you were here, then I would invite you to have a look at the prototypes, the machines that are running over there, right? But if not, you might also step by in my office and look at them there at some point. All right.
So if you want, I can use the camera on this machine. And
oh yeah, I mean, sure, we can do this. We are already a little bit over time,
yeah.
right? But,
are there questions?
Yeah, right. Is there any questions?